In this section, we are going to talk about the periodic table and the discovery of that and how things were organized based off of those discoveries. So Dmitri Mendeleev was a scientist in the 1800s, and he noticed along with some other scientists that there were trends that were happening in different types of compounds and different chemicals. So he noted some repeating properties of some of these compounds based off of their size. And then they started to put together these ideas. So he actually created a card game called Patience, where he put information from the elements on those cards, and then he would kind of try to organize them into some type of a structure or some way to help organize them in some type of classification. So this is one of the earlier versions shown on this slide of where he organized these into various groups. And one of the really parts of his wisdom that I think was demonstrated in his ability to organize these things, he actually left spaces open in certain places because he felt like there's got to be something that maybe goes into this spot, but it hadn't been discovered yet. So he left spaces open so that they could be filled in later once that element was identified. This is, of course, the more modern periodic table that has more of the different rows, periods. We'll talk about those in a second, and some of the parts of those things. We can use this to really understand the distribution of metals, nonmetals, metalloids, understand and balance chemical equations. We can use this table to help us predict and determine chemical or ionic charges and write formulas for ionic compounds. So those are all things that you'll be able to do with this at the end of the semester. So the periodic table is arranged by the atomic number. So you'll notice on the top of each of these different cubes here that represents a different element or a different atom. That's also called the atomic number. The atomic number is the same number as the number of protons that an element has. So the difference between hydrogen and helium is that hydrogen has 1 proton, helium has 2 protons. So that number is both called the atomic number, but it's also the number of protons that are found in those elements. The different rows are called periods. So you have period 1, period 2, period 3, 4, 5, 6, and 7. So the rows go right to left. Those are called periods. And then the columns up and down, those groups are called groups or families. So the way you can kind of think about this is you can think about this is maybe a theater, and this is the front of the stage. And then you would go into the different rows here. You would enter into the different row just like you would at a sports complex or a theater. You'd go into those different rows. And the columns up and down, columns hold things up, right? You think about the columns at the Parthenon, for example, or columns on a building. Those are holding the buildings up, and they go up and down, right? They kind of hold the roof up. So that's how you can kind of remember the difference between a row that you might enter to get into a theater versus a column that's kind of holding a roof up. The different columns are identified by numbers, and you'll notice here we have 1A, 2A, we go to 3A, 4A, 5, 6, 7, 8A, and then we have the 3B, and then it goes through B section. So these are kind of set up a little differently. Those longer and shorter columns kind of can be numbered differently. The standard international way is just to count from left to right all the way across. I just wanted to tell you that so you're aware. Sometimes there are different ways of doing this. We're going to talk about this later in the semester, but I just want to give you a preview so you can kind of recognize this. Really, the difference between the elements is how many protons there are in that element. That changes. Then the number of electrons. Remember, protons are positively charged and electrons are negatively charged. So if we start to add more protons, in order for that compound to stay neutral, we need to add more electrons. As we go down through the rows or the periods of the periodic table, then we start to have to add more electrons to balance out that positive charge of the protons. And you can see here that how we have to add these electrons, it gets more and more and more complex as we go down the periods of the periodic table. So there are some things that we'll talk about why they are the same, but then that also, it changes as we go down and get bigger and bigger in those different periods. So we'll talk about that later. But I just want to give you an idea that the periods, it has something to do and how things behave, have something to do with where those electrons are, how they're organized in the space here. So these different families have different characteristics. So on the left here are the alkali metals and then the alkaline earth metals. And these are all kind of similar here. So helium, lithium, sodium, potassium, rubidium, cesium, francium, those are all similar because I was talking about where those electrons are and how they behave. They have a similar orientation around the nucleus, and that's why they have a similar kind of pattern with how they react. The same with the alkaline earth metals, and then as we move from left to right, we increase the number of protons, we increase the number of electrons around what we call shells, and that's why these families have similar characteristics. So each one of these periods, you can think of it kind of as like an onion, and we have this middle part of the onion, and then as we go down the period, we add another shell, and then we can go down and add another shell, and another shell, and another shell. So those are added on in a way that allow these elements to behave like they do. One note, a lot of the time you'll see this lanthanides and the actinides are underneath, and that's really just to save space. We can, if you actually count, it's 56, 57, 58. This whole group kind of sticks in here, and this thing would extend out. It would be super long. So we kind of pull those out and throw those underneath just to kind of save a little space with our table. So when we look at elements on the periodic table, they're made up of, they might be made up of individual pieces or parts, but when we keep breaking those down into smaller and smaller and smaller bits, they should be made up of only one type of atom. So the simplest forms of matter that we can work with directly, they can make up more complex substances. They're usually more things are made up of multiple complexes of substances that we work with, but there are different types of metals, for example, that can be pure, and we'll talk about some of the differences there. So when we think of an element, those cannot be decomposed or broken down into simpler materials through a chemical reaction. So here is a list of examples of different types of where we get those names from. Some of them, you might look at the periodic table and it's like, why is Na sodium or potassium is a K? So a lot of these are based off of Latin names, where they come from. The Latin name is the corresponding symbol on the periodic table rather than the English name for that typically. So here's some examples of some of these different compounds. For sure, some of the ones you'll get used to kind of naming these. We're not going to have a test where I make you name all of them and memorize those. I'll have a periodic table for most of the quizzes in this course. But what you actually should start to know at least these top 6, 1, 2, 3, 4, 5, 6. These you'll know. Some of these you'll just start to recognize after looking at chemistry material long enough. But these top 4 make up most of what your body is made up of. 96.2% of your body weight is made up of oxygen, carbon, hydrogen, nitrogen. Those 4 are a vast majority of what the elements in your body, and we'll continue to use these throughout courses. You'll see these a lot in biology courses and or biochemistry courses. So these are important to know these because they make up a majority of your body. These next set of slides, I'm going to walk briefly through some of the different families of chemicals. These are, and I'm going to start with the alkali metals on the left side of the periodic table in column 1A or 1. You can see that these are typically basic substances, or sometimes it's referred to as alkali materials, so they're basic compounds, and with the exception of hydrogen. So that is usually these compounds, if they're in solution, they have a higher than 7 pH, which means that they're more basic. And we'll talk later in the semester why hydrogen can probably go really a couple of different places in the periodic table. So this first group, these are typically very reactive, and all of these are metals except for hydrogen is not a metal, it is a non-metal. And we're going to, again, talk about why hydrogen is kind of weird, but we'll get into that a little later. All of these tend to also form +1 ions, +1 ions. Again, we'll get into more of that later in the semester as to why those form +1 ions. And they like to react with oxygen. Obviously, you've probably heard of H2O. Even hydrogen, in this case, likes to react with oxygen. These also do as well. They typically form compounds that will dissolve in water because they do like to tend to form these +1 ions. Positive and negatively charged things can typically dissolve in water, and they usually will form and yield strongly caustic or alkaline solutions, or more basic solutions with pHs higher than 7. The next column on the periodic table is, this is also an A group column, which means it's their taller, longer columns. And they're also typically basic or alkaline compounds with pHs higher than 7 if they're in a water solution. We have beryllium, magnesium, calcium, strontium, barium, radium. Those are all going to be in that column. These earth metals, they're in that second group. Typically very reactive as well as is like the first group. These, however, instead of +1 ions, they form +2 ions. They also like to form compounds with oxygen. These, for example, magnesium oxide, are also strongly alkaline or basic compounds. But these, in contrast, the first column, the second column, are typically not as water soluble. I'm going to move on to, from the first two columns, we're going to switch over to the right side now. And we're going to start with the noble gases. And here's another long, these A groups are typically the longer column groups. And on the far right side of the periodic table, we have the noble gases. And these are going to be very unreactive. So unlike on the left side, on the very right side, these are very inert or unreactive. Only the heavier elements of the group can react. For example, these on the bottom sometimes can react, but it's very often under limited circumstances. And there really aren't that much of these in our environment anyway to even react in the first place. So they kind of have to be forced to react. They don't form charged ions. They are very happy as neutral compounds. And they're typically not going to be grouped up with other gases. So we'll talk about diatomic gases later. But these are monatomic, which means they're just one of them. They don't form, they don't react, they don't interact with other things. So they're pretty happy on their own. When we go over one column to 7A, we have, again, the A group, longer columns. These are the halogens, fluorine, chlorine, bromine, iodine, the astatine. And this was really more of these bottom ones are typically more manufactured in the lab rather than found in the natural environment. These do form diatomic elements, and they are more reactive than their counterparts, the noble gases, just to the right of them. So these are going to be reactive and typically form gases. For example, fluorine, chlorine gases, they'll bond together, they'll form this diatomic element. Bromine is a liquid. Iodine is also a liquid in solutions. So these are typically will be solids or liquids. In contrast to on the left side of the periodic table, the elements on the right side of the periodic table, these are going to form -1 ions. So these will typically form a -1, which means that they will accept an electron to take on a negative charge. So they're pretty happy in that. They'll also make salts with some of the elements we talked about earlier, the alkaline metals. Sodium, for example, they'll form metals with, or metal salts with those elements. So I kind of skipped over the middle, you'll have noticed, and now we're going to kind of go back to this. And these are the shorter columns, and you can see here kind of this is where some of the columns on the right or the left are. And so this was 2A over here, or column 2. And this group here, and we're going to look at the lanthanides are down here, and the actinium, the actinides are over here on the second one. So we kind of cut this region off. I'm not going to talk too much about those. Those are really very rarely used or found on Earth. So we're going to focus more on some of the more common elements that we see in real life. What you'll also notice is some of these are a little different. So we talked about the +1, +2, -1. We'll talk about some of the charges here. Something we should note, that some of these in the middle, these are a little more strange. They're a little more flexible. We're going to talk about that flexibility later in the semester. But iron, for example, some of these will have multiple different charge states they can be in. So iron +2 or +3 means this iron lost 2 electrons or lost 3 electrons. So that can happen. Copper, you'll notice, might be in different charge states as well. For copper over here, we can have manganese found here. It can have multiple different charge states. So these columns will have different, shorter columns will have different possible charge states within here. All of these are metals. They begin in the 4th row. Remember where we have those tall, that's why they're shorter. And then they will tend to form, as I mentioned, several different ions. And down here are the lanthanides and actinides. Their bottom periodic table typically tend to form +2 and +3 ions. The lanthanide elements here, 58 through 71. The actinide, 90 through 103. All of these down here are radioactive, which essentially means that they fall apart. They're such huge, so this means that there are 103 protons in that compound. And when we say something is radioactive, we're just basically saying that those elements fall apart and break down pretty easily because of how big they are. The larger the atomic number, relatively corresponds with how rare that element is in our environment. Chemists like to break these elements down into 3 different broad categories. And one of the categories are metals. And you can see in the green here, these are all metals in this region. The non-metals, hydrogen would count that. Sometimes people put hydrogen over here, and I will do that once in a while, where I'll put hydrogen on top of boron or B. These are non-metals associated with the right side of the periodic table. And then metalloids, like how they sound, have similar characteristics to metals and non-metals. So we have metals on the left side, examples of sodium. Here, lead, Pb, which is found lead, Pb, which is found right here. Iron, Fe, gold, Au. So these are all different types of metals. Non-metals are on the upper right, include oxygen, nitrogen, chlorine. Metalloids are kind of that diagonal strip between. Boron and astatine are 2 examples of that. Properties of metals: they conduct heat and electricity. They're typically solid at room temperature with melting points over 25 degrees Celsius. An example of tungsten's, the melting point's 3,400 degrees Celsius. Mercury is the only liquid metal, the melting point's below freezing, actually. So that's still, even at 0 degrees, it's liquid, which is pretty interesting and unique. The chemical reactivity of those metals, it's a big chunk of the periodic table. So it has a lot of different types of chemical reactivity that reacts. Varies. For example, silver and platinum are very unreactive, but sodium and potassium are very reactive. Just some examples of reactivity differences. Some of the non-metals over here on the right, we have different compounds, and most of them are gases under standard conditions. The monatomic noble, these are gases, noble gases. Some of them are diatomic here in the right side of the period, or in the right side, but over here, not the noble gases. There are a few of them that are solids, and then different forms of certain types, like carbon, for example, can be graphite, coal, diamond. That's all carbon, but they're just in different forms. We'll talk about that later in the semester. Bromine is a liquid. The metalloids, that's this diagonal line here, and they have unique properties: boron, silicon, germanium, arsenic, antimony, and we have tellurium, polonium, astatine. These are all also those metalloids down the center. They're kind of between metals and non-metals. A lot of time they'll have a metallic shine, but they'll be more brittle like a non-metal. And then they're also really good semiconductors, which means they conduct electricity like metals, but not as well. So they kind of have this resistance to that a little bit, and they're valuable as to have different properties to metals. And some examples, a lot of you've maybe heard of silicon chips. They're really valuable to use as semiconductors and to use as chips for electronics.